Today's the only, today's the 15th, so I guess you've officially done your decision?
Yeah.
You do today? Okay. So are you gonna check out Purdue and all before you go there? Or you just
I checked out a month ago.
You went there?
Yeah.
Oh, you went there. Okay. That's cool. Oh, that's right. This is the all right. So let's continue our discussion about dualities. Last time we were trying to figure out, if we did want to solve a linear program and maximize it, and we got some guess for what the answer might be that was feasible, how would we be sure that this answer was in fact the maximum answer? And so we walked through a sort of a reasoning process by saying, okay, how can we recombine inequalities to somehow show that there is no way to get C transpose X to be any bigger than some number? And what we ended up with is that we search for ways to combine inequalities to show that you can't get a number larger than C transpose X is itself another form of a linear program with different variables with the hope that once you solve that linear program, the y values you get are coefficients you can multiply these inequalities by to show that this is wrong. Okay, and so we call one of these a primal and one of these a dual program. And again, sort of the which is primal, which is dual doesn't really matter. The point is these two programs kind of exist together. And the way in which they're connected that I talked about last time was that if we look at, so let x star be sort of the solution that gives you the optimal value here, and y star be the solution here, right? Then it's not hard to show that, first of all, that C transpose x star is less than or equal to y star transpose B. The reason you can show this is because we know that, let's see. So one way to prove this would be to say that, right. So we know that AX is less than or equal to B. That means that Y transpose star AX star is less than or equal to Y transpose star B. But since Y transpose A is greater than or equal to C, then this basically becomes C times X star is less than or equal to Y transpose AX star, which is less than or equal to Y transpose star B. Okay, I should have written Y star transpose, I guess. And then basically show that C transpose X is less than or equal to Y transpose. This is very straightforward, right? I mean, this of course assumes that there exists an optimal value for X star and an optimal value for Y star. That may not always be true, right? We've talked about these LPs that are unbounded, right? In which case, there is no optimal value for X, so that this thing won't work. We've talked about LPs that have no solution, they're infeasible, in which case, again, this won't work. So if both of these linear programs are feasible, then this relationship holds. And again, if you just think about this for a second, if you flip them around, it holds the other way around as well. In other words, what we know, which is what we call strong duality, that it's not just that the primal value is less than or equal to dual value, they're actually equal. And when I think about this, that if you just flip primal and dual, you're saying that they're equal. Okay? So these LPs, this pair of LPs, the primal and dual, are kind of connected in this way, right? So they have this property that, they look different from each other, but they're constructed in almost a syntactic way. You could write a piece of code to take this LP as input and produce that LP as output. It's merely just a transposition of these things. The Y comes in on this side. Right? It's actually not hard to mechanically construct it. But these two LPs work in pairs. Okay? And they work in pairs in an even more interesting way. And one way to see this is that if we say that, so let's say that, so we're going to call this, so this is another feature. It tells you not just that the values are equal, the other two solutions, but that they interact in some way, that the values of the variables interact. Specifically, if we know that C transpose X star is equal to Y star transpose B, what we're basically saying is that C transpose X star minus Y star transpose B is equal to 0, right? And with a bit of algebraic simplification, you can rewrite this as something like Y star transpose times AX star minus B is equal to 0. At the point of equality. And what this is saying is also very interesting, because it's saying that, remember that there's one variable Y for every constraint in X, in AX minus B, right? So what this is saying is that, look, one of these two things has to be 0, which means that if a dual variable is non-zero, the corresponding primal constraint must be tight. It's not just an inequality, it has to be an equality. Conversely, if the dual, if this primal constraint is not tight, this dual variable has to be 0. So in some sense, if you think of our primal problem as as trying to find a point on a polytope that is extreme for a given cost function, right? That point is constructed from certain planes, from certain inequalities. And because that point lies on them, those constraints are tight. So in some sense, the dual is telling you which hyperplanes are participating in a solution. Okay, so again, let's draw this again. We just draw the fragment of the thing where, so then there could be other ones as well, right? So there could be other constraints over here. And if this is the solution to your problem here, then it's saying that the y value, say y1, for each of these constraints must be greater than equal to 0. Oh, if it, well, it can, well, it can, yeah. Well, that's sort of a non-trivial statement, but if those y values are 0, then you must be on that point. And if you have a point on the inside here, right? So it doesn't satisfy the constraint tightly, so it's on the inside here somewhere. Then the corresponding y value will be 0. So the dual value is given an indicator of what primal constraints are found. And for those of you who studied some machine learning and looked at support vector machines, that's kind of what your dual variables give you in there. You give these support vectors. The support vectors are basically value points for which the dual value is 1, so you get someone involved in the actual final output. And this turns out to be very useful because what happens is, when you're trying to solve a linear program, you can basically get a solution that is feasible on the primal side, infeasible on the dual side, and use complementary slackness to adjust the values, so you end up with solutions that are both feasible. And you can see from this that because of this property, that this is always true, if you have a solution to the primal that is feasible, and a solution to the dual that is feasible, they must also both be optimal at the same time because of this property. Okay, so there's a lot of sort of study you can do of the structure of polytopes that comes from thinking about deep learning. Again, this is not something that we're going to do in this class. But the point to keep in mind is that sometimes when you're trying to solve a problem and you can express a linear program, if you write the dual program, which you can write out mechanically and look at it carefully, it gives you a different problem that is somewhat related. And the example we're going to look at now is the example that I've been telling you about for the max flow min cut flow. So what I'm going to do now is I'm going to show you that, in fact, if you write out a linear program for flow and write its dual mechanically like this and stare at it for a bit, what you will realize that is the min cut. And so the fact that max flow and min cut are connected is not some accidental thing. It's a realization of a deeper LP duality that we see. But I couldn't tell you about this if we talked about max flow. So let's do that. So it'll be a good exercise not only to figure out how to write out LPs, but how to write out dual dualities. Right. So let's walk through this sort of carefully. So the first thing we need to do is write down an LP for flow. And that shouldn't be too hard because we've done this kind of thing before. But I'm going to make one small change. Rather than saying that we want to maximize the flow coming out of the source, I'm going to add a sort of a super edge from the sink back to the source and just say I want to maximize the flow coming back on this edge. Because since all the flow goes from the source to the sink, that one edge is going to carry all the flow. That edge has sort of high capacity. So let me walk through this example here. So again, as usual, we have flow on edges. So we have flow on edge UV. And so the goal is going to be, so our variables, flow UV on edge equal to U, V. And the objective is going to be to maximize the flow from T to S. So imagine I have this edge coming back from sink to source, and I want to push over. This allows me to talk about sort of things as circulations, where basically every vortex has to have the same flow coming in. whether it's a source or sink. It's just a nice, easier way of talking instead of distinguishing source and sink. Okay. Then we have constraints. These are the usual constraints. Fij is less than or equal to Cij. Remember, in a maximization problem, we want to maximize something subject to Ax less than or equal to B. So this is kind of the right way of constraints. You want to write things down. This is the constraint here. And the other constraint we're going to say again in a somewhat tricky way. We're going to say that all the flow coming in to a vertex I is at most the flow coming out of the vertex I. In other words, we're going to say something like this. The summation over all j comma I belonging to E flow ji. So this is the flow coming into a vertex I minus the flow coming out is less than equal to for all I for all for all I for all ij. So this is again a somewhat weird way of writing it. All it's saying is that the flow coming in should be less than the flow going out. You could say, well, why less than should it be equal to? But if you write this for every vertex, it's equivalent to saying the flow should be the same coming in. Because if you just keep adding them up, you have ij here and ji here. And of course, the flow value should be 1 to 0. It's a final constraint, which is sort of a default statement that we have. So this is our linear program, and we have to write this dual. Okay. So the first thing you have to do is realize that you need one variable for every dual constraint, every primal constraint. Right? So every primal constraint must be associated with one dual variable. So the real constraints are these two. This doesn't really count. Right? So there are constraints on edges, and there are constraints on vertices, which means you need dual variables for edges and dual variables for vertices. Right? Because if you think of how we look at y, where the y vector is being, there's one y variable for each row of constraint vectors, which means for every constraint. So let's give them names. So we'll say that there are going to be, there's going to be a variable dij, a dual variable dij that's associated with this constraint here. And there's going to be a dual variable pi that's associated with this constraint here. Okay? All right. And just for convenience, we'll put this here. So now, if you think of this in the form maximize C transpose X subject to AX less than equal to B, right? So let's write this. So what does this look like in canonical form? In canonical form, this looks like maximize C transpose X subject to AX less than equal to B, where C is 1. Well, actually it's a 1 and a bunch of zeros, right? The only value in C that is non-zero is the 1 value for FTS. Yeah.
You explain the constraint of the incoming.
Incoming is less than equal to outgoing.
Well, it should be equal.
Yes, but you're doing it because you're doing this for every vertex. It's sort of you could okay. So you could write this as they must be equal. And if you think of how an equality constraint is, all this must be less than equal to, greater than equal to. It turns out it's equivalent to write it this way. This captures it for every single vertex. Because when you essentially sum up these constraints or everything, if it's always less, eventually something will be more. And so you don't want that. So this is a simplification of the standard flow conservation. So again, it takes a bit of a thing, but it's easier to write this in because we want to write this in this less than equal to format here. I could write this in equal to format, then convert the equal to into two less than equal to's and put a minus sign on one of them, and you'll end up with this. So I just sort of jumped a few steps just to get this in this form. Okay. So the first thing is that you have a maximization which should be C transpose X, which means there is one C value for every variable X. The variables X here are the flow values, but the only term in the actual maximization is 1 for FTS. That means the coefficients for all the other flow values are 0. So your C looks like a vector with a bunch of zeros, with just one value for FTS. So you think of all the flow values for each edge, this is one. Okay, so that's C. B, on the other hand, is actually very simple. B is just a bunch of zeros, right there. So keep that in mind. So now we have our dual variables. We know that there are dij's and ti's, and we want to, in the dual formulation, it would be something like minimize y transpose b subject to y transpose a is greater than equal to c, right? Okay, so what does y transpose b look like? So notice that b is not all zeros. I made a mistake. So there's a zeros there, but there's alsocij's up there, right? So this combined with that is your entire b vector. So think of a bunch ofcij's up first and zeros below that. So schematically, if you think of your A matrix, right, we can think of the A matrix as looking like this, right? And there's the X, and there's this, and then there's a bunch of CIJs here, and there's a bunch of zeros here, right? So if you think of the Y values lined up, you'll have all the DIJs here, and then all the PIs here. The DIJs match up with the CIJs, and the PIs match up with the zeros. So if you now look at what Y transpose B is going to look like, it's going to be basically this guy, this vector here, dot product with that. And so you're going to end up with the goal of, now write this in here, maximize sigma Cij, or sorry, minimize dual. Okay. So again, this is purely mechanical. I looked at what the Y looks like, what the B looks like, and just took the dot product because you lined them up that way. Now the way to think of this is that the Dij dual variable should be matched up with what's on the right side of that. The Pi dual variable should be matched up with what's on the right side of that. These are zeros, these are the things, so you get that. Okay. Right now the inequalities is a little bit more work. You have to look at what is the A matrix looking like for this problem. Well, the A matrix looks like a bunch of pluses and minuses. And perhaps the easiest way to think about this is to say, look, if I took a, where does the, I want to know what each of these inequalities looks like. So this times that equals that, right? Okay, so what does this times this look like? Well, this matrix, the rows are the constraints, the columns are the actual edge values, right? So each column is one edge, okay? Which means that each constraint is going to look like a constraint per edge. Which should not be surprising because in the primal, the variable was a variable per edge. So in the dual, the constraint has to be one per edge, just like we did the other way around. Variables become constraints and constraints become variables. So now if you look at this times that, there is some edge here, okay? And the relevant dual variables are going to participate in that. Well, which are the relevant variables for an edge? It's the Pi and Pj associated with that edge and the Dij associated with that edge. Okay, those are the only ones that are going to participate for any particular edge. Okay, so then if you write that down and you just match out the signs correctly, what you'll end up with is something like for all ij not equal to s comma t comma s. Okay. So again, why is that? Remember that in our abstract dual formulation, we come up back here. Each constraint looks like y transpose A is greater than or equal to c, right? So there's one constraint for every primal variable, an edge, and then we need to know what the c value is. But we just observed that for everything except Ts, the c values are 0. So we know that this has to look like a 0 on the right-hand side, and these are the three. There's a Dij for that, and again, you can work this out. You literally just look at the matrix and follow it down for an edge. This is what you'll get. The reason you get minus Pi plus Pj is because this constraint has a minus sign on one of them and a plus sign on the other one. That's why you get like this. All right. Finally, you need one more constraint for Ts. For everything else, it was a 0, but for Ts, the c value is 1. and you end up with PT minus PS is greater than 1. Okay, other way around. Sorry. And as usual, Dij greater than 0. So this right here becomes the dual program corresponding to the primal program that we had from earlier. I don't know yet what this means. This is just a bunch of variables. But if I took my max flow formulation and I wrote down the primal program, okay, and then I did the mechanical dual calculation as I described above, and I produced this object, this is what I get. And so when you do this kind of process, you have to ask, okay, what does this all mean? What is going on? So notice a couple of things, first of all, that you're doing some kind of summation over Cij times Dij. Dij is a variable per edge, and you're minimizing some sum of Cij's, which are capacities of edges. So, okay, I'm summing over capacities of edges. That sounds sort of plausible. Right? And it might help to sort of pretend that this is the integer. Imagine that there are integer constraints associated with this. So imagine that, in fact, you have Dij belongs to 0, 1, and Pi belongs to 0, 1 for a second, just to see what this means. So what does this process mean? Then if you do this, then the only way to set PS and PT is to set PS equal to 1 and PT equal to 0 to satisfy this constraint under this restriction. Okay? But then what does this mean? What does Dij minus Pi plus Pj greater than or equal to 0 mean? Well, PS is 1, PT is 0, and there's a bunch of other things that are 1s and 0s in the middle. So if we look at any particular edge, so let's look at some edge here. So we have I and j, and we know that Dij minus Pi plus Pj must be greater than or equal to 0. What happens if both are 1? If both Pi and Pj are 1, then Dij can be anything, because Dij just needs to be more than 0, which is 1. If both are 0, then again it can be whatever it wants. It doesn't matter. But suppose one of them is 1, one of them is 0. Suppose I is 1 and j is 0. What happens then? So we put a 1 here, we put a 0 here. What can we say about Dij? What must be true for Dij if this is the case to satisfy this inequality?
You defined Dij as a binary value for this example. So somehow you need Dij to be greater than or equal to 1.
So that's be 1.
Right. Yeah.
So if Pi is 1 and Pj is 0, then Dij must be 1. So if we draw these examples here, so we're saying that we have I and j, this is 1, this is 0, and then this value must be 1. If it's 1, it contributes to that overall summation. So it sounds like what we're doing is we are assigning variables to be 1 or 0. Every edge that goes between a 1 and a 0 gets counted in the optimization. And we want to assign 1s and 0s, so the number of edges that get counted weighted by the Cij is as small as possible. But if we assign variables to be 1 and 0, and we know that P of S is equal to 1, we've defined an ST cut. And if we define an ST cut, then Dij is precisely capturing all the edges that go across the cut, which means that this dual program is actually capturing the size of a cut. In fact, and you want to minimize it. So for any consistent assignment of values for Pi to 1 and 0, that the feasible assignment of values will give you a value of a cut, and you want to find the smallest cut. So in other words, if we took the max flow problem, wrote down its linear program, constructed the dual, and interpreted the dual by looking at it carefully what these variables mean, we discover that this is basically the dual program is equal to any questions? Yeah.
In I guess going back to the context of the primal LP program, you wrote Dij and Pi there.
As dual variables associated with the primal constraints.
Right. So these are the primal constraints that we're looking at. Why? How did you? I guess can you just walk me through that again?
Yeah.
What is Dij?
So, if you remember the basic setup here, right? And if you look at the way I've deliberate, that's why I wrote these transposes carefully. If you remember from last time, we were trying to figure out a way to recombine inequalities to argue about what C transpose X could possibly be. And the way we did it is that we assigned a variable per inequality. So there's one dual variable for each primal inequality. Okay? And if you look at this construction, that's exactly what's happening, because if you look at Y transpose, if Y is a vector, Y transpose is like this, and this is my matrix. So there's one variable for each row of A, but each row of A is a constraint. So there's one variable in Y for each constraint. Okay, so that's the basic idea. And dually, for every dual variable, there's one, every dual constraint, there's one primal variable. So primal variables, dual constraints, primal constraints, dual variables. Okay, and they just go back and forth. Max becomes min. Min becomes max. Less than equal becomes greater than equal, and so on. And by the way, a good exercise is to see, is to take that linear program and write its dual. By writing it in canonical form and taking its dual, you should get this back. So the dual is prime. Okay. So having said that, we now come to the actual linear program. And what we said was, okay, we have a bunch of inequalities that describe the primal program. For each inequality, we need to assign a variable. There's one inequality here for each ij pair in E, so you need one dual variable for each. There's one inequality here for each vertex, you need one primal dual variable for each vertex. And you write them down. And if you look at, again, the dual program, which is here, there is one inequality for each edge, which is exactly that constraint there, which corresponds to the dual, which corresponds to the primal variable, Fij. So this dual constraint, if you associate a variable with it, would be some Fij, which is your primal flow variable. Okay. Any questions? So again, what is mechanical about this is converting the primal to the dual. What is not mechanical about this is writing out a good primal and then reinterpreting it. So it's not, these are not automatic things. But once you have a primal, and once you mechanically write the dual, you can, with practice, you will be able to see what the dual is actually saying about the problem, which is, so in some sense, more interesting. Because you're getting structure of the problem. It's almost like I have these two things that don't look related, but if you go to a different level, they are related in this formal way. And that's what's beautiful about duality. That you wouldn't otherwise maybe realize that maximum being cut. And there are lots of other problems like that. For example, in machine learning, you want to find the line separating two sets of points. So let me just draw this out. I won't prove it, but I'll just tell you what it is. So let's say I want to find, I'll get back to this in an example. So in machine learning, you typically have the problem where I have two sets of points, call them blue and red, and I want to separate them by a line. Okay, the easiest case, you want linear classification. And let's say I want a line so that the two are separated as much as possible. It's kind of like a maximum margin separation, they call So think of two parallel lines that together go in the middle and they're as far apart as possible. So in this case, it might look something like this. This is my margin. So I want to get them as far apart as possible, and the classifier itself would be about this middle line. Right? So the atmos separation. This is a very standard question. How do you do the linear separation? Now, even though that problem is not technically speaking a linear program, you can write down a dual formulation for it, turns out. And then if you do the same thing, you write down the dual and then stare at the dual for a while and see what it's telling you, what it's giving you is this different problem. Different problem it's giving you is I have this here, and let's see, I have this here. Okay. And now what I'm going to do is I'm going to construct the convex hull of these 2 points. If you don't know what a convex hull is, it's basically think of a gigantic rubber band. You put it around the points and see where it ends. It's a polygon. Another one here. Okay. And now, given 2 polytopes, my question is very different. My question is, find the 2 points on the 2 polytopes that are closest to each other. Find the closest pair. So the closest pair will probably look like something like this. So it'll be a point on one polytop and maybe a vertex on the other one. In general, that will be the case. It turns out that this is the dual problem, the problem of finding the max. So the find the max margin classifier is the dual of find the points that are closest. Because in a kind of cut, flow, vague sense, the best you can get is the choke point through the polytope, which is the closest pair. And this insight that you can think of this dually as this geometry problem is the basis for many algorithms for solving the original linear classification problem. That rather than trying to find a line, you try to find this closest. So again, the point of LP duality again is to realize that the mechanical process of constructing a dual gives you a connection between 2 problems that otherwise you might not realize are related, and that might give you extra ammunition to try and solve. So there's a whole class of techniques called primal dual methods that basically bounce back and forth from the primal problem to the dual problem to try and get an answer. Again, topic for another class. I feel like I say that a lot. So. Let me go back to max flow and min cut for a little bit. Because I want to go back to this other point of connection. So I talked about how the LP values are the same. So max flow is equal to min cut. But I also talked about one more thing, this idea of complementary slackness. This idea that you can look at the dual variables and the primal constraints and relate them, or the primal variables and the dual constraints and relate them in this manner. And so let's see what that means in the context of. So in the context of flows and cuts, we said that there was a dual variable dij, and there was a primal constraint Fij is less than equal to Cij. Okay? Complementary slackness would say that if this dual variable is non-zero, then this must be tight. Because if this is non-zero, this times this minus that must be 0, therefore this must be 0. So let's see what that means. So let's say, so complementary slackness, so complementary, so the word slackness comes from the fact that if you don't satisfy inequality tightly, it's a slack satisfier. Right? If I'm saying that x is less than or equal to 5, x is 4, I have some slack. So it's not tight. That's where the word slackness comes from. So complementary slackness would say that if dij is greater than 0, this implies that Fij is equal to Cij. But this is very interesting, right? Because if you go back, I don't know if you remember this, but if you go back to when we looked at the proof of Ford-Fulkerson, what we actually ended up showing is that for all edges that go across the cut, the flow is saturated. You cannot push any more flow. What this is saying is the same thing, saying that if I happen to have decided that Dij was more than 0, which means I essentially decided that Ij was in the cut, that the cut was such that Ij went across the cut, then it must be the case that the flow across this edge is saturated. So again, without any knowledge of flows, just looking at the primal, the dual, and complementary slackness, I can derive this property that I know of from proving it more specifically, that the flow is saturated across all edges of the cut. Okay. Maybe a useful exercise is to see what happened the other way around. So let's see. Okay. Okay, yeah. So let's look at this the other way around now. Let's look at an inequality okay. Let's look at this dual inequality. So before I was looking at a primal inequality and a dual variable. Let's look at this dual inequality associated with the primal variable Fij. So let's say we have an edge. So let's say our graph looked like this. It had S was here, and then T was here, and we're looking at an edge that goes from here to here. So it goes from, let's say, K to backwards. Okay. We know that P K must be equal to 0, and P of L is equal to 1, right? Which means that if we think of this edge as Ij, then we have Dij minus 0 plus, I get this order right. Oh yeah, minus 0 plus 1 is greater than or equal to 0. But this means that this inequality is not tight. Right? If Dij minus 0 plus 1 is greater than or equal to 0, then Dij plus 1 is greater than or equal to 0. Whatever Dij is, this is going to be strictly more than 0. So this is strict. If this is strict, then by complementary slackness, this means that the corresponding variable must be 0. Which means that for any edge that goes from the sink to the source, there must be no flow going. So what we've just shown is by complementary slackness that for all edges going from the S side of the cut to the T side of the cut, they're saturated. All edges going from the T side of the cut to the S side of the cut are empty. And if you recall, this is exactly what we had to show to prove that Ford-Fulkerson was wrong. Others couldn't have proven. That allowed us to say that the min cut was equal to the max. So again, the point of this exercise is to show you that you can derive these very specific properties of your solution just by looking at linear programming duality and complementary slackness, which are these sort of more abstract notions. And that what we saw with flows and cuts was really just a special case. It's a sort of easy special case. And so in general, whether it's linear programming or even later on if we do, convex if you study convex programming or other forms of nonlinear programming, there is a way to write a dual. You won't have strong duality, these won't be equal, but there'll be a dual relationship. And there'll be the equivalent of complementary slackness. These are called, Slater's conditions or KPT conditions, things like that. And you can use that to connect properties of the dual to properties of the prime. All right. And that's, basically all I wanted to say about linear programming and duality at this stage. Again, like I said, there's more we can talk about. But for now, I just want to give you this sort of flavor of what linear programming is. So number one, the fact that you can express many problems as an integer program, right, which you can then relax to a linear program and you can round to get an answer. Number two, that this duality relationship between linear programming and its dual allows you to reason about the optimality of a program. It also gives you some structure about your problem that you wouldn't have otherwise had access to if you didn't have this language. All right. I don't want to start something new now, so I'm going to stop here. But I will take questions. Sorry.
Can you scroll up to the diagram of complementary slackness?
The original one?
Yeah, how you explained it. Yeah, this one.
Yeah. So again, the way to think about this is that if you look at this equation here, where they're equal, you get this property here. So what this is saying is that if these are non-zero, the corresponding inequality must be tight. Right? Which means that your optimum solution in the primal is sitting on those hyperplanes. Correspondingly, if this is non-zero, that means you are not sitting on the hyperplanes are not useful. Then the dual variables corresponding to those hyperplanes are zero. So the whole idea of support vectors is, like I said, machine learning is exactly this. The support vectors are the points for which the dual variables are non-zero. The dual variables being non-zero means they participate in the description of the actual hyperplane. In the language of our two polygons in the closest point, the points that participate in that closest pair calculation are the ones that have non-zero dual values. So it gives you a more direct way to go back and forth between primal and dual than just saying the solution to the same value. It actually tells you how to assign the values to it. That's the key. But it's not just saying that the values are equal. It's saying, okay, how do you actually get those solutions that give you that optimum? And then if you think back again, Ford Fulkerson and Max Cut, that's it. Okay. Questions?
So along this line of reasoning, if the optimal dual variable by star transpose is non-zero, we say we have type constraints in primal.
You must have a type. If you have an optimal pair. So in general, right, if you have dual variables that satisfy something, but you don't have sort of a primal optimal solution, then there isn't a pair of solutions to play with. You don't have this relationship. At the point where you have this strong duality, when you get primal feasible, dual feasible solutions, then you get this property here. Right? So typically what's going to happen is you're going to have some infeasible primal solution, and you're going to have some feasible dual solution. The fact that dual is feasible via complementary slackness is going to tell you how to change the primal variables to make them feasible. You're going to make a small change there. That's going to go back into the small change there, and eventually converge to two solutions that satisfy that property. So this property of complementary slackness holds at the optimum point. So it's not only a property of the optimum pair of solutions, it's a way to tell you how to get there. Because in order to get to the optimum, I need this for this to be true. So again, going back to Ford Fulkerson, if I have an edge going out that is not fully saturated, then I can push more flow along it. And only when it's saturated do I get the dual variable. A lot of algorithms will be improved as these primal duals, right?
Can you explain the interpretation of Dij and Pi in terms of part?
Yeah. So, as a mechanical thing, every time you have a primal constraint, you must have a dual variable associated with it. So I just mechanically said, okay, I need one per edge, one per vertex. Fine. Then I say, okay, mechanically, if I have these dual variables, this is what my dual program must look like. And this is a purely syntactic transformation. There is no intelligence in this process. Now I can say, okay, let me look at these things. There's one variable for every edge, that we know, and there's some other variable for every vertex. Okay. We have this constraint that PS minus PT is greater than or equal to 1. And so what I said was, okay, look at the case when these are actually integral values, whether between 0 with a 0 or 1. Instead of being between 0 and 1, there's 0 1. Okay. Notice that there's no reason for them to be very large because you want to minimize. And what we said was, okay, let's take PS and Pi and Pj. They could be two different values. They could be either 0 or 1. If they are both 0, then Dij can be anything. It doesn't tell us anything useful. If they are both 1, Dij can be anything. It doesn't tell us anything useful. But if I is 1 and j is 0, then Dij must be 1. So in some sense, that inequality is encoding the idea that I want to encode the fact that I pick an edge for my cut if one side is 1 and one side is 0. So we talked about this before, how we might do this. This is a way to do this.
Basically, with Pi and Pj, we are assigning values to.
We're essentially using them. So if I told you, hey, go write an LP from in cut, you might say, okay, I have to choose a value to be either 1 or 0. So you might set up your own Pi, 1 or 0. But then you'd have to say, okay, I want to capture only edges that go across the cut. And you have to think very hard to say, how would I write down a constraint that captures the idea that the variable for the edge should be 1 only if it's going on. We spent a lot of time figuring out how to do this. Here, it just got done for us. That's the beauty of this. The dual automatically produced the thing we wanted. It goes this constraint, which enforces that this is 1 whenever these two are different. It has to be. And then automatically you just add up the things that are 1. So it's kind of cool, right? Instead of having to work on the constraint ourselves, because of duality, it just kind of made it happen. Magic. So that's the interpretation of Dij. Dij is essentially an indicator variable saying, did you pick this edge for the cut or not? Pi is an indicator variable saying, is this on one side of the cut or not? The constraint is, I can only pick an edge for the cut if one side was 1 and one side was 0. And that's what we do. That make sense? Yeah. And duality is it's a beautiful thing because a lot of things fall out of the dual sort of by magic, just by doing that operation. Because there's some underlying geometry that's being captured there. You didn't see it. This is an example of just sort of magically moves out. So it's a good tool to have to explore. It's good to have to wield a bit of magic. Game of Thrones as well. No dragons though. Okay. Any other questions? Okay, I'll have a final, very short assignment on things relating to linear programming and optimization. It should be out tonight. It'll be short because you don't have a lot of time for it. But it'll be, hopefully, it'll sort of go over some of the basics of everything else. You can fully expect that at some point I might say, okay, construct a dual this linear programming. You have to practice everything. So this is the kind of thing that I'll be asking you to sort of get some practice. Okay. All right. I will see you all on Wednesday.